Long before anyone understood what the sky was made of, people lay flat on the ground and watched it move. Not metaphorically flat, actually flat. On stone, on grass, on the decks of ships crossing water so wide that the horizon curved visibly on every side. They watched the stars rise from one edge of the world and set at the other, tracing their slow arcs through the dark, returning to the same positions night after night, with a reliability that nothing else in their lives could match. Crops failed, rivers flooded, rulers died and were replaced. The stars came back. What none of them could have known, what no one knew in any civilization for the entire length of recorded history, was that they were lying inside a disk, that the sky wheeling above them was not a dome, not a ceiling, not a fabric stretched between pillars at the edge of the earth. It was the interior view of a flat spinning structure, 4.5 billion years old, and they were pressed against its surface the way a coin presses against the bottom of a bowl of water, looking out through the water rather than down at themselves from above. Every astronomer who ever lived until very recently shared that view. Ptolemy in Alexandria in the 2nd century, cataloguing stars by brightness and position without any way to know their distances. The Arab scholars who preserved his work and extended it through centuries when much else was being lost. Galileo, who in 1609 pointed a curved piece of glass at the moon and saw mountains casting actual shadows, not symbols of mountains, not a smooth celestial sphere, but rock and relief, and the ordinary physics of light falling at an angle. All of them were looking sideways through the disk, from inside it, the way you look along the surface of a table rather than down at it from above. The Polynesian navigators who crossed the Pacific were doing the same thing, and doing it with a precision that approached something closer to a working relationship with the sky than most of what we call science. They read the rising and setting points of stars the way you might read a compass, not because they had studied the geometry, but because the geometry had been memorized across generations, passed from one careful mind to the next, tested every time a canoe left sight of land, and had to find it again on the other side of open water. The disk held their stars in reliable positions. The disk kept its word. They trusted it the way you trust a road you have walked 1,000 times. None of them were wrong about what they needed. The stars were where they said. The bearings held. The canoes arrived, but all of them, every navigator, every scribe, every person who ever lay on their back on a clear night and let their eyes move with the rotation, were looking at the flat plane from inside it. Sideways, always sideways. There is a reason for that, and it has to do with where we are in the galaxy, not just the solar system. The disk of our solar system does not lie flat within the Milky Way. It tilts. The plane the planets share is angled at roughly 60 degrees to the plane of the galaxy itself, a steep lean, more like a ramp than a shelf. This means that the direction we call above the solar system, the direction off the disk, points partly toward the space ahead of us as we travel through the galaxy, and partly toward the space to the side. We are not a still object, we are part of a current. The sun carries everything with it around the center of the galaxy at roughly 230 kilometers every second. One full circuit takes somewhere close to 225 million years, a span of time that has its own name, the galactic year, though no civilization has ever lived through one. The last time the solar system sat in exactly the position it occupies tonight, the most complex things walking the surface of this planet were early dinosaurs. The oceans held different coastlines. The continents were arranged differently. Nothing that would recognize its own reflection had yet appeared. And through all of that, through every galactic year, through every generation of every species that has come and gone on this particular planet, the disk has held its shape. The planets have kept their orbits. The flat sheet has remained flat. The sideways view has remained the only view. An Egyptian scribe lying on a rooftop 2,000 years ago, watching the stars rise over the Nile, was looking at the same disk from the same angle you would see it from tonight. The geometry between that rooftop and the sky has not changed in any way that matters on human timescales. Only the watchers have changed, and even then, in the ways that count, lying still and watching the sky turn only slightly. That continuity is worth holding for a moment before the journey moves on from it. Every person who has ever felt small under a clear sky, every child who has looked up and felt the particular mix of comfort and vertigo that comes from realizing how much is out there, all of them were inside the disk. All of them were looking along its surface. None of them were above it. The view from above has been waiting through all of it, patient as the sky tends to be. The reason no spacecraft has ever climbed directly above the solar system is not a failure of imagination. The designs exist. The calculations have been done. The reason is something more fundamental, a wall built into the physics of where we were born, invisible and total, that every serious mission concept has had to find a way around. You are carrying that wall with you right now. Everything in the solar system, every planet, every moon, every fragment of rock and ice that orbits the sun, inherited its motion from the spinning cloud that formed this system 4.5 billion years ago. When that cloud collapsed under its own gravity, it began to rotate. As it shrank, it rotated faster, the way a skater pulls her arms inward and accelerates. The spin flattened it into a disk, and everything that condensed out of that disk, including the Earth, including you, inherited the disk's sideways motion as a permanent condition of existence. Earth moves around the sun at roughly 30 kilometers every second. That number is difficult to feel. It corresponds to about 67,000 miles per hour, which is fast enough that the distance between two major cities passes beneath you in the time it takes to finish a slow breath. You feel none of it because everything around you is moving at exactly the same speed, in the same direction. The motion has no texture. It is simply the baseline condition of being here. That baseline is a gift when you want to go sideways. To send a probe to Mars, you only need to adjust your speed by roughly 4 kilometers per second, a nudge forward along the track, changing your orbit just enough to intersect Mars's path at the right moment. The 30 kilometers per second you already carry does most of the work. The rocket only has to fine-tune what the solar system already gave you. To go straight up, the 30 kilometers per second becomes the problem. Up, in the specific sense of off the disk, perpendicular to the plane the planets share, uses none of the speed you inherited. That motion runs sideways. It does nothing for you when the direction you want is at a right angle to it. Before you can begin to climb, you have to cancel it, erase approximately 30 kilometers per second of inherited velocity, built up over 4.5 billion years of the solar system's existence before a single meter of altitude above the disk is possible. The energy cost of doing that by direct thrust is close to 10 times what it costs to reach Mars. A rocket powerful enough to cancel 30 kilometers per second of sideways motion and then still have something left. For the climb would need to carry a quantity of fuel that no conceivable launch system can lift off the ground. The wall is not made of distance, it is made of momentum. Here is one way to feel the scale of it. Pluto sits roughly 5.5 billion kilometers from the Sun. It is the frozen edge of the familiar solar system, so far that sunlight takes more than 5 hours to reach it, so cold that nitrogen freezes on its surface like frost on a window. New Horizons flew there in 9 years, traveling most of that distance on the momentum inherited from its launch and a gravity assist from Jupiter. By any ordinary measure, Pluto is remote. A point directly above the Sun's north pole, only a few million kilometers up. A tiny fraction of the distance to Pluto requires more energy to reach than Pluto does. The far edge of the solar system is easier to touch than the air above our own star. We are not walled in by distance, we are walled in by our own speed. This is why no mission has ever simply aimed upward and fired. The fuel needed to cancel 30 kilometers per second by brute force does not exist in any launchable form. Every real design, every probe concept that has ever been seriously studied, every trajectory that has been calculated and found workable, gets around the wall the same way. It does not fight the inherited speed directly. It steals momentum from something larger. Jupiter is the obvious candidate. The largest planet in the solar system carries enough gravitational influence that a probe passing close to it can use the planet's own orbital motion to dramatically change its trajectory. Ulysses, the first spacecraft ever sent to fly over the sun's poles, did exactly this. Launched in 1990, it traveled outward to Jupiter first, let the giant planet's gravity bend its path, and emerged from that encounter tilted nearly 80 degrees out of the plane it had started in. It did not fight its inherited sideways speed. It traded that speed for a different kind of motion, one that carried it over the poles of the sun on a path no spacecraft had traveled before. There is another approach, slower and stranger, that requires no fuel at all beyond what sunlight provides. A solar sail, a large, thin reflective surface that catches the faint pressure of photons leaving the sun, can gradually shift its orbit over months and years, winding its path higher and higher above the disk, the way a spiral staircase climbs a column. The climb is patient. It cannot be hurried, but it costs nothing except time. And time is something the sun has in abundance. The wall is real. The solutions to it are real. They are just indirect, requiring the patience to fall before climbing, or the willingness to borrow what cannot be earned by force. The disk holds you with a grip 4.5 billion years old. The way out begins by accepting that. The first machine to fly over the sun's poles did not go there directly. It went to Jupiter first. Ulysses launched in October 1990, a joint mission between NASA and the European Space Agency, carrying instruments designed to measure the solar wind, magnetic fields, and particle environments in a region of the solar system that no probe had ever entered. It carried no camera capable of photographing the sun's poles. The poles were not the picture. They were the destination, and the instruments aboard were tuned to feel what was there rather than see it. The journey to Jupiter took just over a year. In February 1992, Ulysses made its closest approach to the giant planet. Swinging through the powerful gravitational field at precisely the angle the mission planners had calculated, Jupiter's gravity bent the spacecraft's path sharply out of the ecliptic plane, hurling it southward and upward in a trajectory that no rocket fuel alone could have produced. The probe emerged from the encounter on a course that would carry it first over the sun's south pole, then north across the equator, then over the North Pole, a path that no human-made object had ever traced. What Ulysses found above the poles was different from what the equatorial regions of the sun produce. Down in the plane, the region where the planets live, where everything we had ever measured before was measured, the solar wind blows in a variable, gusty stream. It carries the sun's material outward at speeds that shift and surge, tangled in magnetic structures and disrupted by the complex activity near the solar equator. It is not a smooth flow. It is something more like weather. Above the poles, the wind changed character entirely. Ulysses measured a flow running at roughly 750 kilometers every second, nearly double the speed of the slower equatorial wind. It was steadier, cleaner, less tangled. The fast polar stream blew outward with a consistency that the equatorial measurements had not prepared the mission's scientists for. The poles of the sun were not calmer than the equatorial regions. They were faster, more organized, driven by a different kind of magnetic structure than what the planets experience in the plane. Ulysses flew over both poles 3 separate times across more than 18 years of operation. Each pass added detail to a picture that had existed before only in theoretical models. The probe measured the polar regions in ways no instrument had managed. It felt the fast wind. It traced the magnetic field lines threading out from the poles into interplanetary space. It gathered data that reshaped the understanding of how that sun influences the bubble of space it inhabits, and it never photographed any of it. Not once in 18 years of operation above and around the sun's poles did a camera image come back showing what the poles looked like. Ulysses carried no instrument capable of that. The data arrived in numbers, particle counts, magnetic field vectors, wind velocities, is assembled into models by scientists who had to imagine the picture from the measurements the way a blind person might build an understanding of a face through touch. The shape was there in the data, the image was not. For 35 years after Ulysses, that remained the situation. Then Solar Orbiter began its slow climb. The European Space Agency launched Solar Orbiter in February 2020 on a trajectory that would take it progressively closer to the Sun, while gradually tipping its orbit out of the ecliptic plane. The tipping was not immediate. It could not be. Each Venus flyby, and the mission used several, transferred a small amount of orbital inclination, trading one kind of motion for another, climbing away from the disk, in careful increments, the way water rises through a lock rather than rushing over a dam. By early 2025, Solar Orbiter had accumulated enough inclination to attempt what no spacecraft had managed before. In the middle of March 2025, the spacecraft tilted its view toward the Sun's south pole, from an angle of roughly 17 degrees below the solar equator. It was not directly above the pole, not the clean overhead view that future missions aim for, but it was far enough off the equatorial plane to see past the limb of the Sun, to look down at a region that every previous instrument had seen only edge on or not at all. The images came back. They were the first photographs of a pole of our own star in the entire history of the species. Carol Munell, the European Space Agency's Director of Science, said it plainly when the images were released. Humankind was seeing its own star's pole for the first time. Every photograph taken before that moment, from Galileo's first rough sketches of sunspots to the sharpest modern solar observatory images, had been taken from somewhere near the solar equator. The Earth and every telescope ever launched from it were trapped in the disk's plane, looking at the Sun from the side, the way you might study a coin, by holding it at eye level and never turning it face up. The face the Sun finally turned toward the camera did not look like the equatorial face. The orderly bands and structured regions visible from the side gave way to something more tangled. South Pole showed a chaotic knot of magnetic activity, north and south polarities sitting alongside each other in the same region, jumbled in a way that the smoother equatorial images had not suggested. It was the fingerprint of a star near the peak of its 11-year activity cycle, gathering itself toward the magnetic flip that happens at every solar maximum, when the north and south poles of the Sun swap their polarities entirely. That flip begins at the poles. It had been studied through its effects on the solar wind and the particles reaching Earth. It had never been watched from a vantage point close enough to see the mechanism directly. Solar Orbiter was not close enough to watch it directly either. Not yet, but it was close enough to see that the roof of our own star was not what the models drawn from equatorial observations had drawn. The tangled magnetic field at the South Pole did not match the predictions that decades of sideways observation had produced. The first view from above was also the first clear indication that the sideways view had been incomplete in ways that could not have been fully known until a different angle was achieved. Right now, as you are resting, the Sun's poles continue to burn in the pattern Solar Orbiter captured, a pattern no eye had seen before last year, a pattern that instruments spent decades slowly climbing into position to reach. The light leaving those poles crosses space at the same speed all light travels. Some of it, scattering outward, is already beyond the orbit of Pluto. Some of it is still crossing the inner solar system. Some of it, if you were outside on the right kind of clear day, is arriving. It arrives whether or not we have instruments ready to receive it. It has been arriving since long before we did. Everything you have ever known exists inside a bubble, not a metaphor for a bubble. An actual structure, a region of space carved out by the Sun's own wind, pushed outward in every direction against the thin gas that fills the space between stars. The solar wind streams away from the Sun continuously, carrying charged particles at hundreds of kilometers per second, and where that wind finally meets the pressure of interstellar space and can push no further, the boundary forms. Inside, everything, every planet, every moon, every probe we have ever launched, every signal we have ever sent. Outside, the galaxy proper, the space between stars, the material that was there before our sun ignited. The bubble has a name. Scientists call it the heliosphere. It is the sun's sphere of influence, in the most literal physical sense. The region where the sun's output still dominates, where the solar wind still runs the show before the interstellar medium finally pushes back hard enough to stop it. The boundary itself is called the heliopause. Cross it, and you have left the solar system in the deepest sense of the term, not just past the planets, not just past the Kuiper belt, but past the sun's own reach. 2 spacecraft have crossed it. Voyager 1 reached the heliopause in 2012. Voyager 2 followed in 2018. Both had been traveling since 1977, launched on trajectories that took them past Jupiter and Saturn, and, in Voyager 2's case, Uranus and Neptune as well. By the time they reached the heliopause, the engineers who had built them were retired or had died. The students who had studied them in graduate school were grandparents. The probes kept going indifferent to all of it, transmitting data home on signals that take more than 20 hours to arrive. They crossed the heliopause, but they crossed it sideways. Both Voyager probes travel nearly flat within the disk, close to the plane of the ecliptic, skimming along the sheet the planets share rather than climbing above it. Their crossings of the heliopause told us about the boundary at 2 specific points, 2 narrow samples of a structure that wraps around the entire solar system in 3 dimensions. The shape of the whole bubble, the true form of the heliosphere seen from outside, that remains something neither Voyager could show. They were inside the room, feeling 2 points on one wall. The view from above the room, the view that would show the room's actual shape, was not something they could take. For decades, the textbooks drew the heliosphere as a comet shape, a rounded head facing the direction the solar system travels through the galaxy, and a long tail streaming behind, blown back by the pressure of interstellar space. It was a reasonable picture. It matched the intuition that an object moving through a medium ought to leave a wake. It appeared in textbooks and lecture slides, and popular science illustrations for long enough that it began to feel like established fact rather than inference. In 2020, a team led by Merav Ofer at Boston University ran a fresh analysis of NASA particle data and arrived at a different shape entirely. The particles near the edge of the heliosphere picked up ions, originally interstellar material caught and carried in the outer boundary regions, appeared to leak away too quickly to be consistent with a long tail. In the model Ofer's team found most consistent with the data, the heliosphere looks less like a comet and more like a shape with 2 curved jets extending from its sides and no significant tail behind. Some descriptions compare it to a deflated croissant. Others find different language for the same general idea. A puffed center, asymmetric, with structure on the sides where the tail was supposed to be. Other research teams still argue for the tail. The debate is genuine, ongoing, and unresolved. There is no consensus on the shape of the bubble we live inside. The honest position, if you read the current literature carefully, is that we do not know. Not approximately know, not know with some uncertainty, genuinely do not know. The shape of our own home, the structure that has been carrying everything we are through the galaxy for 4.5 billion years, remains an open question. The reason is simple and a little strange once you sit with it. We have never seen the heliosphere from outside. Every measurement ever made of the heliosphere was made from within it. Every model of its shape is built from particles counted inside the boundary, from magnetic field measurements taken by spacecraft that never left the region they were trying to describe. It is like trying to determine the shape of a building by standing inside it and listening to the echoes. Useful, genuinely informative, but not the same as walking outside and looking at the walls. A newer mission named IMAP, the Interstellar Mapping and Acceleration Probe, launched in September 2025 and stationed itself out past the Moon, in a position where it can map the boundary with greater sensitivity than previous instruments. IMAP does not leave the heliosphere. It maps from inside, using energetic neutral atoms that pass through the boundary and carry information about conditions on both sides. It is a more sophisticated version of the listening approach. Better ears, better processing, a richer echo to work with, but it is still inside the room. The view that would settle the question. The view from above the disk, looking down on the heliosphere the way you look down on an island from altitude, seeing its actual shape spread out below, has never been possible. It requires a probe that has done what no probe has fully done, climbed high enough above the ecliptic plane to see the bubble from outside its own equatorial cross-section. There is something quietly unusual about this. If you let yourself feel it, you were born inside this structure. Every human being who has ever lived was born inside it. Every animal, every plant, every microorganism that has ever existed on this planet spent its entire existence inside the heliosphere, protected by the sun's wind from the full intensity of interstellar space. The bubble has been home longer than home has had that word. It existed before the Earth was solid, before the oceans formed, before the first chemistry that eventually became life began its slow experiments in shallow water. And we still do not know its shape. There is something that feels almost right about that. Not troubling, just honest. The oldest home is also, in a specific and verifiable sense, still incompletely known. The child who grew up in a house and never once saw it from the street. The instruments that might finally show us are being built. The window to use them is opening. That is where the story goes next. The window does not stay open forever. This is something worth understanding before the journey moves further. Not as urgency, but as context. The current moment in the exploration of the solar system's vertical dimension is the product of a convergence that was not arranged deliberately and will not repeat on any timescale that maps onto human planning. It is a coincidence of readiness, instruments arriving, angles improving, techniques maturing, all at roughly the same time. Solar Orbiter is climbing. Each Venus flyby adds a few more degrees of inclination, tipping the spacecraft's orbit further from the equatorial plane, buying a slightly better angle on the poles with each pass. The climb is slow by any instinctive measure, years between each incremental gain, but it is steady and the trajectory is fixed. The spacecraft will continue to rise above the plane for the remainder of its mission, eventually reaching inclinations that will allow it to see the poles at angles that the March 2025 images only approximated. The full picture is being assembled one careful degree at a time. Future instruments will have capabilities that Solar Orbiter does not. The Nancy Grace Roman Space Telescope, expected to reach its operating position by 2027, carries a coronagraph designed for the kind of precise starlight suppression that direct imaging of faint structures requires. Roman's primary mission is not solar science, it is wide-field astronomy, the mapping of dark energy, the study of exoplanets across large portions of the sky. But the coronagraphic technology it carries represents a generation of improvement over what came before, and the techniques developed for Roman will feed directly into whatever comes next for direct imaging of the solar neighborhood. Ground-based telescopes with mirrors exceeding 30 meters are under construction at several sites. When they come online, they will bring angular resolution and light-gathering capacity that no current instrument can approach. Objects and structures that sit below the detection threshold of everything operating today will become visible. The improvement is not incremental. It is a step change, the kind that opens new categories of observation rather than simply refining existing ones. And then there is the question of how a probe actually gets above the plane. The Oberth maneuver is the answer that keeps appearing in every serious design study. Hermann Oberth described the underlying principle in 1929. A rocket engine fired at the lowest point of a deep dive into a gravity well produces far more useful energy than the same engine fired anywhere else. The physics is the same as the reason a pendulum swings highest when released from height. The deeper the dive, the faster the object moves at the bottom, and the more efficiently a thrust at that moment translates into trajectory change. A probe designed to climb above the solar plane would fall inward first, not toward the sun in a catastrophic sense, but in a controlled, calculated arc that brings the spacecraft within a few solar radii of the sun's surface, screaming through the bottom of the deepest gravity well in the solar system at well over 100 kilometers per second. At that one moment, at the point of closest approach, the engine fires. The velocity gained from the dive multiplies the effectiveness of the burn in a way that no amount of fuel expended in flat space could match. The fall becomes the launch pad. The dive generates the climb. Project Lyra, a concept developed to study trajectories for reaching interstellar objects passing through the solar system, uses this same principle. The interstellar probe concepts studied at the Johns Hopkins Applied Physics Laboratory return to it repeatedly. Every serious calculation of how to escape the disk's plane in a reasonable time frame arrives at the same counterintuitive answer. You go toward the sun before you go away from it. You fall before you fly. The solar sail alternative takes longer and asks for a different kind of patience. A sail large enough and light enough to be meaningfully pushed by photon pressure. The faint, continuous nudge of sunlight can gradually spiral its orbit upward over years, winding away from the plane without consuming any fuel. No violent burn, no close solar pass, no single critical moment when everything depends on an engine firing correctly at a specific instant. Just the slow, patient accumulation of a force so small it cannot be felt, over a period long enough for that small force to become a significant displacement. Both approaches work, both have been studied, neither has been funded for a dedicated polar mission. What has been built, and what is operating now, represents the first serious foothold. Solar Orbiter's images from March 2025 opened a door that had been theoretically possible for decades, but practically closed until the spacecraft completed enough of its slow climb to reach a useful angle. The data from Ulysses, measured without photographs, felt without being seen, built the scientific case that made Solar Orbiter's mission worth funding. Each generation of instruments has made the next one possible. The current decade sits in a particular position within this progression. The angles are better than they were 10 years ago. The instruments are more capable than they were 20 years ago. The theoretical framework for what should be above the poles, the fast wind, the magnetic flip mechanism, the connection between polar structure and the heliosphere's shape, is more developed than it has ever been. Questions that could not be precisely formulated a generation ago can now be asked in forms that an instrument could, in principle, answer. The next set of answers is being assembled. Some of it is already in transit, data collected and not yet fully analyzed, models running on observations still being calibrated. Some of it depends on spacecraft that have not yet launched, on observations that have not yet been scheduled, on a probe that has not yet been designed for the specific purpose of climbing above the disk and looking down. The window for all of this is not closing, but it is particular to this time, this set of tools, this moment in the long history of looking upward. What those tools might eventually show is worth imagining even before they show it. That is where the story arrives next, not at a confirmed answer, but at the shape of what the answer might be, and what it would mean to finally hold it. There is a particular kind of knowledge that comes only from the outside. You can know a great deal about a place while living inside it. You can map its corridors, measure its temperature, count what moves through it, and record how fast. You can build models of its structure from the inside out, refining them as new data arrives, arguing over details, converging gradually on something that resembles a true picture. This is not a lesser kind of knowing. It is the kind we have, and it has produced everything we understand about the solar system, about the planets, the sun, the wind that flows between them, the boundary where the sun's influence finally runs out. But there is something the inside view cannot give you: the shape, the whole shape seen at once, from a distance that contains it, the view that shows not just the parts but the proportion, how much of the structure faces the direction of travel, how the tail compares to the head, if a tail exists at all, whether the bubble sits symmetrically or leans, whether the poles are compressed or extended relative to the equatorial regions. These are not small details. They determine how the heliosphere protects what lives inside it, how it interacts with the interstellar medium, how the sun's wind distributes itself in 3 dimensions across the full structure of the region we call home. Every generation of people who has ever looked at the night sky has been inside this structure without knowing its shape. The navigators in their canoes, the scribes on their rooftops, the engineers who built Ulysses and watched its data arrive for 18 years. All of them were inside the same bubble, all of them contributing to a picture of the inside that grew more detailed with time. None of them, none of us, ever above it, long enough to see the outside of the walls. The first solar orbiter images changed something, but not everything. They showed the poles at an angle. They revealed that the inside of the sun's roof looked different from what the sideways view had suggested. They established, quietly and without drama, that the picture assembled from equatorial observation was incomplete in ways that only a different angle could expose. That is a significant thing. It is not the same as the full outside view. The full outside view remains ahead. What comes with it, when it comes, is not just an image. It is a correction or a confirmation of everything the inside measurements have suggested. It is the moment when the model built from echoes is checked against the actual shape of the room. Sometimes those checks find that the model was essentially right, that the echoes were faithful enough to the walls, that the reconstruction was accurate. Sometimes they find something different. The history of science is full of both outcomes, and there is no reliable way from inside to know in advance which one is waiting. There is something gently worth holding in that uncertainty. Every grandmother who ever pointed upward at the night sky, every parent who has stood with child on a dark evening and tried to find words for what the stars are and how far away they go, was pointing at the ceiling of a room whose walls and floor and true shape none of them had ever seen. The wonder they were gesturing toward was real. The pointing was accurate. The star was there, and the distance was real, and the feeling that something vast and patient was out there was not wrong. It was just incomplete, as all knowledge held at any moment turns out to be. The thread that connects a Polynesian navigator reading the stars from an open canoe to a spacecraft scientist watching solar orbiter's first pole images arrive on a screen in a control room is not the sophistication of the instruments, it is the direction of the attention. Both were looking up in the sense that matters, not at what was immediately useful, not at what was near, but at the thing beyond the near, the thing that was there whether or not anyone was looking at it. The navigator needed the bearing, the scientist needed the data, but both were, in some quieter way, doing the same thing, paying careful attention to something that had been there long before the attention arrived, and would be there long after it moved on. The heliosphere has been carrying us through the galaxy for 4.5 billion years. It was doing this before there were eyes to notice it. It will continue after the instruments currently measuring it have gone dark, after the missions that succeeded them have also ended, after whatever follows those has run its course. The bubble is not waiting to be understood. It simply continues, pressing its boundary against the interstellar medium, channeling the fast wind down from the poles, holding the shape that 4.5 billion years of the sun's output has carved into the space around it. We are the ones who are waiting for the angle to improve, for the instruments to arrive, for the probe that will fall toward the sun and then climb, carrying a camera above the plane for the first time, sending back the image that no previous generation had the tools to take. It is coming. Not tonight, not in the next few years, but within the reach of people alive right now. Within the span of missions already being designed and funded and argued over in meeting rooms, where the windows look out on an ordinary sky. The question has waited this long. It can hold a little longer, and in the holding, there is something that is not quite patience and not quite peace, but sits somewhere between them. The particular quality of a question that is old enough and deep enough that it has stopped being anxious about its own answer. The disk holds everything. The bubble holds the disk. The galaxy holds the bubble, carrying it on a spiral path at 230 kilometers every second, through space that was old before the sun ignited, and somewhere above all of it, above the plane, above the poles, in the clear space where the zodiacal dust thins and the fast polar wind flows, and no camera has yet turned to look back down, the view is waiting, unhurried, as everything at this scale tends to be. The sky tonight looks the same as it always has. That is not a small thing. It is, in a way, the most important thing about this particular journey, that at the end of it, the view from the ground has not changed. The stars are where they were. The disk is holding its plane. It's the same night it would have been for anyone who stood outside 10,000 years ago and let their eyes adjust to the dark. What has changed is what the sky contains for someone who has spent time thinking carefully about what they are looking at. The flat plane overhead is not just a backdrop for the stars. It is the surface of a structure, a disk 4.5 billion years old, thin relative to its width, holding every planet and moon and drifting comet in the same ancient inherited motion. The stars you can see with your eyes are all inside that disk in a broader sense, all riding the same galactic current, all part of the same slow spiral, through a galaxy that contains them the way the heliosphere contains the solar system. A larger bubble holding a smaller one, and larger structures still holding those. The person who lay on the grass as a child and felt the vertigo of looking up into too much space, who felt the ground become uncertain beneath them because the sky was so large and so indifferent to the smallness of a single human body lying at its edge, that person was not wrong about what they felt. The scale is real. The indifference is real, in the sense that the universe does not organize itself around any particular point of observation. The feeling was accurate. What that child could not have known, lying there, was that they were inside a bubble whose shape we still do not know, that the flat disk they were pressed against, invisible beneath them, in the sense that you cannot see the floor of the room you are standing in, had never been photographed from above, that the star at the center of it all had poles that no human eye had seen until last year, that the spacecraft measuring the boundary of our home were traveling sideways across it, crossing one wall and telling us about that one point, while the full shape of the structure remained and remains genuinely open. The grass is still there. The vertigo is still available. The child can still lie on the ground and feel it. But now the feeling has a more specific geography. The disk presses you sideways through the galaxy at 230 kilometers every second. The bubble around you has been carved by the sun's wind over billions of years, and its shape is being argued over right now in papers and conference presentations and careful exchanges between researchers who have spent their careers on this one question. The poles of the sun, burning in a pattern that no photograph had ever captured before March 2025, are above and below you in the most literal sense, directly over the sun's north and south, in the direction off the disk, in the only direction that has remained almost entirely unseen. All of that is present in the sky tonight, whether or not the sky shows it. The navigator in the canoe did not need to know the heliosphere existed to use the stars correctly. The bearing was real. The star was steady. The knowledge that served the crossing was complete enough for what the crossing required. That is still true. Looking up at a clear sky and feeling something, continuity, scale, the particular quality of attention that darkness and stars tend to produce, does not require any of this to be known. The feeling does not depend on the facts. But the facts do not diminish the feeling. That is the other thing worth saying. At the end of a long journey through the physics of an invisible disk and an unseen bubble, and the first photographs of a star's pole. The facts do not make the sky smaller. They make it more specifically itself, more precisely what it actually is, rather than a general impression of vastness. The disk is 4.5 billion years old and holds everything. The bubble is older than the oceans, and its shape is still being determined. The poles of the sun burned in a tangled magnetic pattern that no model had drawn correctly, and a spacecraft spent years climbing slowly into position to see them. And the images that came back were the first of their kind, the history of a species that has been looking up for as long as it has existed. The sky tonight contains all of that. It is the same sky. It is holding more than it ever has, somewhere above the plane, in the direction that has no name in most languages, in the space over the sun's north pole where the fast wind flows and the zodiacal dust thins, and the view of the disk would finally open below a camera that has not yet arrived. The light continues. It has been continuing all along. The ground is steady beneath you now. The disk holds. Above the plane, the dust thins. The fine material that fills the disk, the ground-down remnants of comets and broken asteroids, the accumulated debris of 4.5 billion years of collisions and slow dispersal, settles in the flat sheet with everything else. Rise above it, and the haze that softens the inner solar system from within begins to fall away. The view clears, the stars sharpen. The disk below spreads out the way a landscape spreads when you climb high enough to see its edges. No camera has held that view yet. The bubble presses its boundary against the interstellar medium in every direction, patient and continuous, the oldest structure we have ever lived inside. Its shape is still being worked out by people who spend their days reading particle data and running models and arguing carefully over what the numbers mean. The argument is not finished. The shape is not confirmed. The home we were born into is still, in this one specific sense, partially unknown to the people living in it. That will change. Not tonight, not in the next few years, but within the reach of instruments being designed now, within the span of missions that exist as calculations and proposals and careful conversations about what is worth the cost of going there. The view will come. A probe will fall toward the sun and climb. A camera will rise above the disk for the first time. The image that every generation before this one lacked the tools to take will eventually be taken. And the sun's poles will continue burning in their tangled magnetic pattern, slowly gathering toward the flip that reshapes the heliosphere's structure every 11 years, indifferent to whether any instrument is watching, patient in the way that only things measured in billions of years can be patient. The stars are where they always are. The disk holds everything, still and ancient, carrying its motion in through the dark. The light keeps traveling.